In the vast silence of space, stars are born. They shine for millions or billions of years, and eventually, they die. But not all stellar deaths happen alone. Many stars live in pairs, gravitationally bound companions orbiting each other in a delicate cosmic dance. And when one, or both, approach the end of their lives, that dance can turn violent. Two collapsing stellar cores spiraling inward, two white dwarfs feeding off one another, two neutron stars smashing together at a fraction of the speed of light. These are not science fiction catastrophes. They are real astrophysical events, observed, measured, and studied. Tonight, we explore what truly happens when dying stars collide and why these events help shape the very elements that make up our world. Most stars are not alone. Binary star systems are common throughout the Milky Way. Astronomical surveys show that roughly half of Sun-like stars and the majority of high-mass stars exist in binary or multi-star systems. This matters because stellar evolution is not just about internal nuclear fusion, it's also about gravity between companions. As stars age, they change size dramatically. A star like our Sun will eventually expand into a red giant, growing hundreds of times larger than its current radius. If its companion star orbits nearby, the expanding outer layers can spill over, transferring mass from one star to the other. This process is called mass transfer, and in some systems, it destabilizes the orbit entirely. When that happens, a merger becomes inevitable. When two white dwarfs merge. White dwarf stars are the dense cores left behind when medium-mass stars exhaust their nuclear fuel. They are about the size of Earth, but contain nearly the mass of the Sun. Their matter is supported by electron degeneracy pressure, a quantum mechanical effect. Now imagine two of these remnants orbiting each other. As they spiral inward, they emit gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. Over millions or billions of years, those waves drain orbital energy. Eventually, the two white dwarfs merge. If their combined mass exceeds approximately 1.4 times the mass of the Sun, known as the Chandrasekhar limit, the merged core becomes unstable. The result? A Type 1a supernova. Type 1a supernova. This explosion completely disrupts the star, leaving no compact remnant behind. Type 1a supernovae are critical in cosmology because their peak brightness is relatively consistent. Astronomers use them as standard candles to measure cosmic distances. In fact, observations of distant Type 1a supernovae led to the discovery that the expansion of the universe is accelerating. Neutron star collisions. When massive stars, much larger than our Sun, explode as supernovae, their cores can collapse into neutron star objects. Neutron stars are extraordinarily dense. A teaspoon of neutron star material would weigh billions of tons on Earth. When two neutron stars orbit each other, gravitational wave emission becomes significant, especially in their final moments. In 2017, scientists detected gravitational waves from a neutron star merger for the first time. The event known as GW170817 was observed in both gravitational waves and electromagnetic radiation. This marked the beginning of multi-messenger astronomy, combining different types of signals to study cosmic events. When neutron stars collide, they eject neutron-rich matter into space. Heavy elements form via rapid neutron capture, or R process nucleosynthesis, and a bright transient called a kilonova occurs. Kilonova. Gold, platinum, uranium, many of the heaviest elements in the periodic table are believed to originate in these collisions. The merger remnant may become a heavier neutron star or a black hole if the mass exceeds stability limits. The common envelope phase. When a red giant expands enough to engulf its companion, the system enters what astronomers call the common envelope phase. Inside this shared gaseous envelope, drag forces remove orbital energy, the cores spiral closer together, and the outer envelope may be ejected. If the cores merge, the result can be a more massive single star. Some mergers produce a luminous transient event known as a luminous red nova, less energetic than a supernova, but brighter than a classical nova. One well-documented example is V1309 Scorpii, which provided strong evidence that luminous red novae are stellar mergers in action. Direct star collisions in dense clusters. In most of the Milky Way, stars are so far apart that direct collisions are extremely rare. However, in dense environments, such as globular clusters, stars can pass close enough to merge. In these clusters, stellar interactions can produce unusual objects, including blue straggler stars, stars that appear younger and hotter than the rest of the cluster. Many astronomers believe blue stragglers form through stellar mergers or mass transfer in binary systems. Gravitational waves and Einstein. All of these collisions share a common signature, gravitational waves. First predicted by Albert Einstein in 1916, gravitational waves were directly detected a century later. Their discovery confirmed a key prediction of general relativity and opened a new observational window into the universe. Unlike light, gravitational waves pass through matter almost unimpeded, carrying direct information about violent cosmic events. Without them, neutron-star mergers would have remained partially hidden. What star collisions do not do? It's important to clarify, star collisions do not routinely destroy galaxies. They are not common random impacts across interstellar space. They do not create universe-ending chain reactions. Most occur in pre-existing binary systems where orbital decay makes merger inevitable. Hollywood often exaggerates their frequency and scale. Astrophysics relies on measurable data, spectra, light curves, gravitational wave signals, not dramatic assumptions. Why these collisions matter? When dying stars collide, they create heavy elements, form black holes, produce gravitational waves, reshape binary star populations, and influence galaxy evolution. Our own planet contains elements forged in ancient stellar explosions and likely neutron star mergers. The gold in jewelry, the uranium in Earth's crust, the platinum in electronics. These atoms were born in catastrophic stellar events billions of years ago. Closing. From destruction to creation. Narrator. Slower. Reflective. In space, destruction and creation are inseparable. When dying stars collide, they unleash extraordinary energy, yet they also seed the cosmos with the building blocks of future worlds. These events are not chaotic accidents, they are natural consequences of gravity, nuclear physics, and time. The universe evolves through cycles: birth, fusion, collapse, collision, renewal. And in the echoes of gravitational waves traveling across billions of light years, we are witnessing the final moments of stars and the beginning of something new.